All right, let's pull back the curtain on one of the most transformative technologies of our time, machine learning. We're going to see how we've taught computers to stop just following instructions and to start actually learning for themselves.
You know, let's start with a little piece of everyday magic we all kind of take for granted. You say a couple of words, and boom, your phone wakes up, ready to go. But have you ever really stopped to think about what is actually happening in that split second?
Get this. That's about how many audio samples your phone's microphone is grabbing every single second. It's just this constant flood of noise. And out of all that digital chaos, it has to find one very specific, very tiny pattern. Your voice saying that exact phrase. I mean, how is that even possible?
Well, here's the thing. You can't program it the old way. See, for something like a shopping cart on a website, a programmer can write out simple, explicit rules. If a user clicks Add to Cart, then add the item. Easy enough. But for recognizing a wake word, you'd have to write a rule for every voice, every accent, every possible bit of background noise. The list would be literally infinite. You just can't do it.
And that challenge, that impossibility, it forces us into a totally new way of thinking about programming. It takes us right to the big idea behind machine learning, which is this huge shift from writing rules to instead learning from data.
So here's the crucial part. We're not trying to teach the computer what Hey Siri sounds like. That's the impossible task, right? Now, instead, we build a program that can teach itself how to recognize it just by seeing tons and tons of examples. We're not teaching it the answer. We're teaching it how to learn.
And that, right there, brings us to the formal definition. Machine learning is really all about creating these algorithms that just get better and better at a task simply by being exposed to more and more data. The more it sees, the smarter it gets. It's that simple.
Okay, so let's really dive into this. If we're not writing rules, what exactly are we doing? Well, let's look at the actual recipe that makes this whole learning process work. It really just boils down to 4 key ingredients. You know, from a bird's eye view, it's a pretty simple loop. We start with a model that's basically a blank slate. It's clueless. We show it some data, see how it does, and then we make a tiny little adjustment to make it a bit better. The magic is that we do this over and over, millions, sometimes billions of times, and it gets just a little bit smarter with every single step.
So ingredient number 1 is, of course, data. This is the fuel for the whole engine. For our Hey Siri example, this would be thousands and thousands of little audio clips, and each one is carefully labeled by a person as either, yep, that's the wake word, or nope, that's not it. Second, we need a model. Now think of this like a really complex but very flexible machine. Its behavior isn't set in stone. It's controlled by millions of tiny digital knobs or parameters. Our job is to find the perfect setting for all of those knobs.
Third, how do we know if a setting is any good? Well, we need a scorecard, and that's the objective function, sometimes called a loss function. It takes the model's guess, compares it to the correct answer from our data, and it spits out a score that tells us exactly how wrong it was. The goal is always to get that score, that loss, as low as possible.
And finally, ingredient number 4 is the learning algorithm itself. This is the engine that drives the whole process. It looks at that score from the objective function and automatically figures out which way to turn each of those millions of knobs just a tiny bit to make the score go down. And then it does it all over again.
So now we have our 4-part recipe, right? Data, model, objective function, and an algorithm. So what kind of stuff can we actually build with it? Turns out, this basic framework can be used to solve a huge range of problems.
The most common approach, by far, is something called supervised learning. This is what we've been talking about with Siri. It's supervised because we're like a teacher, standing over the model, giving it a massive data set of questions that also have all the correct answers. We're supervising it as it learns the patterns.
And what's really cool is that most of these supervised learning problems boil down to one of 2 really simple questions. Are you trying to predict a number, or are you trying to predict a category? That's pretty much it.
The difference is really straightforward. Predicting a house price in dollars, that's a continuous value, right? That's a regression problem. It answers how much. But deciding if a photo is a cat or a dog, that's a distinct category. That's a classification problem. It's just answering which one. Now, supervised learning is definitely the dominant player here, making up most of what you see out there. But it's not the only game in town. You've also got unsupervised learning. That's where you give the model data with no labels and just ask it to find interesting patterns. And there's also reinforcement learning, where a computer agent learns by trial and error,
kind of like how you'd teach it to play a video game. So a lot of these core ideas, they've actually been around for decades, which raises a really big question. What changed? Why has machine learning, and especially this subfield called deep learning, suddenly just exploded into the mainstream?
Well, the answer is basically a perfect storm of two things happening at once. First, the internet gave us data on a scale that was totally unimaginable before. And second, kind of funny, the video game industry accidentally gave us the perfect tool to process it all. Those powerful graphics cards, GPUs, which just happen to be amazing at the kind of math you need for machine learning.
And this table, wow, it really puts that growth into perspective. Just look at the scale. We went from kilobytes to terabytes of data. But even crazier is the compute power. We went from megaflops to petaflops. That is a 100 million-fold increase in calculations per second. This massive shift in resources just unlocked totally new possibilities.
And the main thing it unlocked was the true potential of deep learning, which is a specific type of machine learning that uses these really complex, multi-layered models called neural networks. And this has been the real game changer.
Okay, if you only take one single thing away from this entire explainer, please let it be this. The truly revolutionary idea behind all of modern AI is this concept of end-to-end training.
Here's what that means. In the old days, a human expert, a PhD, would have to spend months or even years handcrafting special programs to look at an image and pull out what they thought were important features, like edges or textures. Then, a simple AI model could make a guess. With deep learning, forget all that. We just feed the raw pixels in one end, and we get the answer cat out the other. The model learns to figure out what the important features are all by itself, in one big, unified end-to-end process.
This ability to learn directly from raw data, it is a monumental shift. It completely changes the game. It replaces all that painstaking human work with pure computational power, leaving us with one final and really exciting question to think about.